وهدى من الرحمن يهدينا به.
Hello, please. Welcome to Photochemistry. First of all, we're going to look at the following. We're going to look at the definition. We're going to see photochemical versus thermochemical reactions, and then laws of photochemistry, and then how radiations are absorbed. So to begin with, we're going to start with the definition, and we're saying that photochemistry is a branch of chemistry which deals with the study of chemical reactions taking place due to exposure of the system to light radiations whose wavelength lie in the UV visible region. And here the UV visible region is 200 to 800 nanometers. Or we can simply say that is the study of chemical reactions that proceed with the absorption of light radiations by atoms or molecules. So we can easily define it that way. In short, we get to know that photochemistry cannot occur without light. So for it to occur, the molecules or atoms should absorb the light radiations. Okay? And then these radiations should have at least the wavelength of the specific, they should be having specific wavelength corresponding to the electronic transition taking place in that particular reaction. Okay? So let's look at the examples of photochemistry. Okay, we know very well that for photosynthesis to occur, light must be there. And we can also have it in phototropism, which is the movement of plants towards the light source. Okay, we can also have it in Judaism. Actually, this one is a yellow coloration, which we normally see in newly born babies, and we normally see this yellow color around maybe the skin, the eyes, okay, and mouth also. And we can treat this color by using, we can get rid of this yellowish color by using a blue light in the wavelength of 430 to 490 nanometers. Okay, we can use even direct sunlight, but to use this one we have to use a wave filter so that it can eliminate the harmful waves. Okay, so we can use it also in photography. Of course, photography cannot occur without light. We have it in formation of ozone layer. Okay, and also in vision, of course, we cannot see without light. We use light to see, and many other applications of photochemistry. Okay, so let's look at the differences between thermal and photochemical reactions. First of all, we have the thermal reactions. The first one here we have for thermal reactions. These reactions involve absorption of heat. Okay? For these reactions to occur, we need to absorb some heat. While for photochemical reactions, these ones we need to absorb light. But don't forget which light. It should be the light of specific wavelength corresponding to the electronic transition taking place in that specific reaction. And then another one, they can take place in the dark provided that we have heat. Reactions, thermochemical reactions can take place. And also On the side of photochemical reactions, the presence of light is so important. So for photochemical reactions, they can take place. They have to occur in the presence of light. And then here we have temperature is significant effect on the rate. So here for thermochemical reactions, the rate is being affected by the temperature, while for photochemical reactions, the rate is being affected by the intensity, by the light intensity. And then for thermochemical reactions, of course, here we normally see the Gibbs free energy, the delta G, is negative. In other words, here the reactions here spontaneous, you have spontaneous reaction, while here the delta G can be either positive or negative. In other words, it can be either spontaneous or non-spontaneous. And then the last one here, the activation energy is acquired by absorption of what? Of heat. While on the other side, the absorption energy is acquired by absorption of photons. So now let's look at some of the some of the laws. We have, first of all, we have the laws of photochemistry. We have the Grothaus-Dropper law, and this one, it states that only those radiations which are absorbed by a reacting substance are responsible or effective in producing chemical changes. So this one, what does it mean? It means that the light that gets reflected or transmitted, that light will not produce any chemical change. So that light which is reflected or transmitted will not have any effect on chemical change. Now let's look at the Stark-Einstein law. This one states that each molecule absorbs a single photon of light in primary process. So each photon absorbs a single photon of light in a primary process. So here the primary process would mean at the beginning of a reaction. So it means that at the beginning of a reaction, each molecule will absorb only one single photon. So as we're going to take A as a molecule, and then this one is a photon. We're taking this one to be as a single photon, so the reaction proceeds in this way. A will acquire a photon, and then it's going to be represented as A star. Okay? But for intense lasers, in case we use intense lasers, okay, this one will be, it can absorb more than one photon. So in other words, it can be A, and then if it is to absorb maybe two photons, in case we use intense lasers, so here it's going to be two photons, okay, to absorb two photons. So it's going to be represented as A star star. That's when we use intense lasers. Okay, so here we're taking the V as a frequency of the absorbed photon, and the energy of the absorbed photon is represented as this one here. So we say that V is the frequency, so H, we know it is known to all of us that that's the Planck's constant. Okay, so now let's look at what is next after this proton absorbing the energy. So we have two alternatives. The activated molecule may undergo a chain of mechanism whereby large molecules may undergo reaction. Okay? And also the molecule, alternatively, the activated molecule may deactivate without any reaction. Actually, we're going to see all these two alternatives. We're going to see all this in our next episode. Okay, now let's look at the absorption of radiations. The Auger's law or Lambert's law states that the intensity of transmitted light decreases exponentially when the thickness of the substance through which the light is passing through increases linearly. So it means that whenever we increase the thickness, we are decreasing the intensity of light that is being transmitted. Okay. So now here, sorry for that. Now here, in short, we get to know that the intensity is number of photons interacting in a unit time. Okay. So we have the law. This law can be represented mathematically as log I naught. I means the intensity before the light passes through the sample, and then I, the intensity of light after passing through the sample. Okay. And K here is the constant. We're going to take it as a constant of our sample. And then B is the thickness. Okay. As we're seeing here, this one is light, the intensity of light before passing through the sample, and this one's the thickness. Actually, we normally take the thickness. This one is constant. Normally use 1 centimeter. We use the cuvette is normally 1 centimeter, and then this one's the intensity of light after passing through the sample. Now you see, it has been decreased. So here at first we had the intensity is a bit high, but after passing through the sample, okay, it has been decreased. Okay. So now let's look at the Bayes' law. So this one, the intensity of transmitted light decreases exponentially as the thickness, as the concentration of the absorbing substance increases. So whenever here we increase the concentration, we're decreasing the intensity of transmitted light. Okay. And also this one's represented as log I naught divided by I, which is equivalent to K. You see here K is the constant, divided by 2.303 constant. Okay. And here this cuvette, it is the cuvette is the one that we use in the lab. It's being represented as here. This one is the intensity before, then intensity after. Okay. So mathematically we can combine the two laws and represent them as follows. So here A stands for constant called absorptivity. Okay. This one is the constant called absorptivity, and B is the thickness, and then C is the concentration of the absorbing species. Okay. So now if we take the concentration as grams per decimeter cube, and then C, B in centimeter, so the unit A is going to be, will have this kind of units. Okay, this is the unit of A. In case we have, as you remember, concentrations, mass over volume. So this one is mass, and then the volume. Okay, the B is, so when we try to get the units of B of A is going to be direct units of A. Okay. But for the concentration, whereby the concentration is expressed in mole per decimeter cubed, and D in centimeter, the absorptivity for this case is going to be called a molar absorptivity, and is expressed as epsilon. Okay, epsilon, and has a unit of, these are the units of the epsilon, which is the molar absorptivity. So we can represent the molar absorptivity as in this law, whereby A, log I naught divided by I is equivalent to epsilon. B, C, epsilon, we say it's molar absorptivity, and B is the thickness, and then C is the concentration, okay, of the sample in moles, in concentration per mole decimeter cubed. And then the term log I naught divided by I is called absorbency and is represented as A. So A is equivalent to this one, so whereby we can say that A is equivalent to this log I naught divided by I, or log I naught divided by I is equivalent to A. So it's the same thing. So we can, instead of writing log, we can put here A. Okay, this A we can put it here, and we proceed with our calculations. Okay, it means that A here stands for absorbency. So we can say, we can eliminate this and then say that absorbency, okay, is equivalent to ABC, or we can say absorbency is equivalent to E epsilon BC, and we proceed with our calculations. Okay, so as we say, this one's absorbency, the molecular absorptivity, the path length, and then here the concentration. So please, thank you so much for watching. Thank you so much for your time. Let's meet in another episode. Have a good day.